Okay, once again, do you have any? Is there any question from others? Okay, so we can move to the sixth presenter, Aulia Rahman, with the title of the paper is objective comparative study of object detection models for dense coffee bean defect detection using YOLOv11, faster RCNN, and RetinaNet. Yes, you can share your
Okay,
presentation.
thank you so much, Mr. Wayu. I'll be the presenter for this, Mr.
Okay.
Aulia. Okay, please. Mhm. Okay, I just want to make sure if my screen is already presenting
Yes,
or
I can see
okay.
your screen. Good.
So, uh, good morning, everyone. My name is Zaki Alfitra, and I'm from the University of Shakwala. I'm with my other three authors, which is Mr. Aulia Rahman. Have joined this session already, and Mr. Rafal Tirta Mufti, and then Mr. Huajen Yap. Uh, I'll be presenting this paper for our study, which is the title is Comparative Study of Object Detection Models for YOLOv11, Faster RCNN, and RetinaNet. Okay, so let's we get started. Okay, so our motivation is we all know that coffee is the major global commodity in Brazil, Vietnam, Colombia, and Indonesia. But many of those industry globally is still uses the manual inspection. But the problem is manual inspection. It is lack of consistency. It is labor intensive, subjective, and as I say, inconsistent at higher scale. And it is also more prone to fatigue because it's reducing accuracy. And also, defect severity also determines its grade. Even these slight defects, it's affecting the overall market. So that's why we wanted to make the detection for defects of coffee bean severity. Okay. So the problem and our research gap is existing method of CNN classification is require pre-segmented or isolated beans, and it barely work on densely packed that we tested on this paper or overlapping coffee beans. And there's slight or no systematic comparison exists between one-stage detectors like a YOLO and RetinaNet, and also two-stage detectors such as faster RCNN for dense multi-objects. And crowd orientation is overly expensive. Labeling hundred of overlapping objects very much is also time consuming, and that's why we are modifying our own method, which is Mosaic pack augmentation. Uh, so our contribution here is, of course, a systematic comparison between five object detection for densely packed coffee beans using the evaluation metrics such as precision, recall, F1 score, MAP 50, and MAP 95. Also, we evaluate under a complex multi-object condition using dataset generated with Mosaic pack augmentation. And we also identify the most suitable models for this type of problem or cases, and we try which is the best of it. Okay, so this is our method pipeline. As we can see here, we need to gather data, which is we uses 70% of training data and 20% of validate data, and then the rest of it, the 10% of uh, the tested data. Uh, so for the after the data collection, and we pass it into the image pre-processing and also mosaic augmentation approaches, and then after that, if when we get all the image after processing augmented, we pass it into the five models, and then we train the model, and those models, we validate them, and then we test it on the dense bean coffee. Okay, so our dataset consists of 8 classes, which is normal, and 7 other defects, which is black, sour, broken, Haas, foreign matters such as rock or stick. If you can see on the screen, this is the foreign stick, and this is the foreign for the rock, and both of them is uh, what is it is uh, classes into just one class, and then also slight insect and severe insect. Our capture setup, we uses the Fujifilm X-T4 camera to the white A4 paper, and we arrange the coffee beans into 9 times 6 grid, and we support it in with ring light and enclosed booth. So the original split data is 70% of train, as we said before, and then we generate the augmented data. This is the augmented basic, not the Mosaic pack, and we have the additional 5,000 images, and then we have the total image of 9,397 of images. So we're gonna explain a little bit about our proposed Mosaic pack augmentation. So we found when we do our researches with standard Mosaic, or with the Mosaic that has been researched by other people, the standard Mosaic is quite struggle with multi coffee beans images, uh, because standard Mosaic, just like Mosaic 4 or Mosaic 9, is just taking those image and then just putting there on into a grid without cropping this uh, background or something. And our method is we do exactly the same as standard Mosaic, but we add additional cropping into the image. So we remove the unnecessary background, because in real world cases the beans is closest to each other, right? Okay, so the method is single beans crops based on their labels to remove background, and we pack them row wise into 64 by 64 canvas without overlapping. If you can see, there is no cutting to the image bin, so it's clearly places in the canvas. For the density, we uses the 4 to 134 bins per generated image, so it is more replicating into real world cases. Okay, so after we generate them, we have the total image of the Mosaic pack augmentation is 1,350 total, which is 1,000 of them is train image, and 250 is validation, and the rest of it is the test image. Okay, so we compared 5 models here, which is YOLOv11 nano version, the large version, and the extra large version, and also we add additional models from PyTorch library, which is RetinaNet and faster RTNN, because we chose them because at the time this is the most popular models out there. So for the training configuration, we uses the 100 epochs with SGD optimizer and momentum 0.9. For the input image, we use 64 by 64 pixels image, so it's all the same image, even with the Mosaic pack is 64 by 64 pixels. For the batch size, we use this difference from here with YOLO and those PyTorch models. we uses the batch size of 30 to 40 YOLO and the 4 for the RetinaNet and faster RTNN, because we have been fine-tuned for each model and chooses the best hyperparameter configuration for each model. For the learning rate, we also uses the difference from YOLO and the PyTorch models. For the YOLO, we uses the 1 times 10 to the power m minus 3, and for the others is 10 to the minus of 2. For the hardware, we uses the NVIDIA RTX 6000 8th generation, which uses the 48 gigabit of VRAM, so it is capable of training these models. And the result is for the 5 models, we can see we have highlighted the best result from each models. If you can see here, for the F1 score, is the best is the large model, and for the precision is the extra large version. And for the fastest models, here is the YOLOv11 nano version. And the key takeaways is YOLOv11 large version is offer the best accuracy per speed, which is achieve 81.5% of MAP50. And I'm sorry about it. For the YOLOv11 large is achieving the best F1 score, which is 80.4%, and for the YOLOv11 extra large wins in the MAP, which is 67.3%. But the trade-off is the higher compute cost. And for the RetinaNet, has the weakest precision, which is 67.2%. This is the visualization from our dataset. This is the test dataset, and it is different. We don't use this in the training dataset. We uses the training dataset with the Mosaic pack, and then we test it in this real-world scene or real-world cases. So we have highlighted with red circle here, and for the YOLOv11 large or extra large version is the most closely matched to the ground truth, and with minimal miss detection. And for the YOLOv11 nano version and RetinaNet has the highest miss detection or miss classification. So our conclusion here, we are come out with the conclusion for recommended or most balanced performance per compute cost per the inference speed is the YOLOv11 large version, because it's give the good performance and also really low inference speed, and that's why we say that the best accuracy per speed trade-off. And for the maximum accuracy, we uses the YOLOv11 extra large version because it achieved the highest MAP50 and 95. But the trade-off is the raw speed is quite slow. It at 35.2 millisecond of inference speed. And for the edge deployment, we suggest the uses for nano version because it's achieved the fastest inference speed, but also doesn't really good at performance, but it's still acceptable, I think. So I think that's it for our presentation. Maybe our limitation is here. We uses the dataset is just lab control, so we are not using the public dataset. We uses all our dataset for by ourselves. We take those photos, and then for our future work, maybe we can do a video-based inspection for a conveyor system for a real-time grading system. Okay, I think that's it. 10 minutes. All right. Okay. Sorry, you still muted.
Oh yeah, sorry. Thank you very much for the presentation. Is there
Okay.
any question from other participants in this room? Okay, I may have one question. So what is the actually what is the motivation as your study? Because yeah, in my opinion, and I would like I have two questions actually. What is the your motivation in this study, and the second, what is the method? This what is the traditional method to select a good coffee bean and not good coffee bean?
Um. Okay, so I will answer for the first question first. Okay.
Yeah,
Um. Our motivation here, right? I'm sorry. Can you repeat the first question?
yeah. Okay. What is your motivation? What is your
Okay.
motivation of the present study?
So, um, as I said before in the second slide, that we see in the former, in Indonesia, especially in Takengon Aceh, uh, w- w- uh, we see that many of the industries in Indonesia, especially, is still um, they still uses the manual inspection.
Okay.
Um, because of that, we are motivating to implement our knowledge with the um, computer vision to solve that problem. Because manual inspection, we know that uses a lot of people to do the inspection, and also if you know, like
Yes.
manual sorting problem, and
Okay.
this research can solve the two problems, which is manual sorting and then manual inspection. Manual
Understand.
inspection is
Okay.
uses for people to
Understand.
determines grades of coffee beans, and
Very
manual
very
the
good.
sorting problem is for
Yeah.
uses the farmers, right?
Okay.
Okay,
But
so
currently you are still using a PC, right? Personal computer, right? For
yeah,
doing.
yeah, we train and we tested in our computer.
So no, I mean, how do you? What is your plan? Because you cannot bring your computer to the farmer and to
Oh yeah.
test. What is your
um, so
next?
our
Yeah.
plan is we uses the fastest, as we say, the fastest model, and then we applied it into the edge device, such as Raspberry Pi or Jetson Nano, I guess, and we sell them maybe into the farmer or the inspection people.
Okay.
And then
Thank you
for
very
the
much.
second question, if
I think you
for
already answered this my second question.
oh,
What is the traditional methods? Yeah, you already answered it.
okay, okay,
They use yeah using the conventional one.
okay,
Okay, thank you very much, Mr. Zaki
okay.
Alfitra, for the presentation.
Thank
And
you, Miss.
to call the next presenter,
Uh,
Ana Nur